this to a whole number ratio. And of course you know, because you're all advanced math students, that you're going to multiply that by 2 and actually get a 5:2 ratio. So it might be x5, y2, or if substance y came first, y2, x5, depending on the information in the problem. So kind of keep an eye out for that as a next step. Alrighty, moving on to test hint number 23, because you'll again have several problems like that one in a row. How to determine the empirical formula of a that was 21. How to write the formula of a binary ionic compound. This is monster, 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 monster. If it's an ionic compound, you need to identify the charge on the metal, here's one, and the charge on the nonmetal or the polyatomic ion that it's attached to. You are going to crisscross those charges and use those as your subscripts. For example, in potassium sulfate, if we go to the periodic table, we know that potassium's in column 1 valence electron that it would be willing to lose, plus 1 oxidation state or charge for a potassium ion. Sulfate, as a group altogether, has a charge of -2. That is one of the inis, SO4, the sulfate ion, one of the inis in the polyatomic ion pattern that I showed you to help you remember them. Make sure you memorize them. Get on the flashcards and Quizlet games on Moodle and practice, practice, practice if you don't know them yet. You need to recognize that that is a -2 charge. And because that's a -2 charge overall, and potassium's only +1, we're going to need another positively charged particle. Also note that this charge becomes that subscript, and if we consider sulfate altogether, that charge becomes that subscript. We just don't write it if it's a 1. Pen casts on that, plenty of practice. You guys picked it up right away. I don't think you're going to have problems with that part. All right, 24, 25, 26, 27, 28. This is all about naming compounds, whether there's something with a polyatomic ion and a transition or heavy metal where you're going to need a Roman numeral, or it's a molecular compound where you're going to use the prefixes like carbon tetrachloride here, or the stock system, carbon Roman numeral 4 chloride, and it's going to kind of give you a couple ionic compounds and then a couple covalent compounds. Practice your monster. Practice your monster. I don't think you're going to find that part too challenging, so I'm going to move right on. Test hint number 29, and let's see, 29 and 30. Again, some information or questions on asking you for the name. These are both molecular compounds where you're going to need the dis and tris. Remember, ionics never try to die. Covalents or moleculars are always dying to try. We put those prefixes in there. And this part of the test is going to kind of cycle over. Give you some practice writing names and formulas, either naming compounds or writing the chemical formulas, whether it's molecular or ionic, and then we'll get back to something on the oxidation numbers, identifying them. You should have a good handle on the rules because we've been doing that for a couple chapters now. And there's a couple questions where I might ask you for one of the rules, like, you know, what's the oxidation number of a monatomic ion? Well, that equals its charge. Or what's the oxidation number of, like, oxygen? Because it's typically -2. Hydrogen, typically +2 unless it's combined with the metal, then it's, or sorry, +1. Unless it's combined with the metal, then it's -1 instead. They add up to 0 overall unless it's a polyatomic ion, adds up to the charge. If you can write formulas, you know those rules. Just think about what the question is actually asking. Alright, 32 is another naming with the stock system. 33, how to calculate the molar mass of a binary ionic compound. Again, you're just adding the atomic masses. So our iron 3 chloride here is a binary ionic compound. I'm going to look up the atomic mass of iron, add it to 3 times the atomic mass of chlorine. Boom, there you go. 34 is asking you to calculate the number of moles in a given mass of a compound. So this is where you're going to need to know the molar mass. And in this particular problem, we actually give you the molar mass so that you don't have to spend your time adding up the atomic masses of the compound. Elements in the compound. You can just jump ahead and do the actual problem. This is where you're going to be using your train tracks or your factor label method to help you cancel. In the Brightstorm videos, you've seen numerous examples of these. Let's say, for example, we have, I don't know, 150.00 grams of calcium carbonate. Well, we know, do it this way, train tracks, that 1 mole of calcium carbonate is roughly 100.087 grams. Very simply divide the mass given by the molar mass to get moles. If you are given moles to start with, you're going to flip this conversion factor. You'd be multiplying by atomic mass to get, or molar mass to get grams. Test hint number 35 is a question that is just like the one I just mentioned. 36, how to determine the number of ions present in a specific number of moles of a compound. Well, let's take a look at calcium carbonate. How many ions of calcium are in a mole of calcium carbonate? If you break this down and look at the subscript, there is 1 mole of calcium ions in 1 mole of calcium carbonate. There's also 1 mole of carbonate ions. In my copper phosphate example here, there are 3 moles of copper ions, 2 moles of phosphate ions. Put that number to start in your problem and then do your calculation from there. These are very simple, straightforward conversion problems. If you set them up using train tracks or the factor label method and cancel units top and bottom, and make sure your conversion factors are written out. Notice the number 1 is attached to mole in the conversion factor. Big, dramatic, and exciting number 1. You're not throwing Avogadro's number in there unless it is specifically asking for particles. And then you still have 1 attached to mole and then 6 times 10 to the 23rd particles in there. But most of the problems are not about that. They're about going from moles to grams, grams to moles. 37, how to calculate the percent composition of a given binary ionic compound. I'll go back to my iron 3 chloride here. What is the percent of iron? What is the percent of chlorine? We're going to take the atomic mass of our 1 atom of iron divided by the molar mass of the whole substance times 100. Or if we're asked to find chlorine, I'm going to take 3 times the atomic mass of chlorine divided by the molar mass of the whole compound. If you're asked to give the percentages of both elements, just do one calculation and, of course, subtract from 100 to get the other one. Test hint number 38, how to define empirical formula. Simplest whole number ratio of the atoms in a compound. Easy peasy. 39, how to calculate empirical formula of a binary ion compound when given mass percentages of the elements. I've already done a sample problem like that with the carbon and hydrogen. This is going to be a similar one that's maybe an ionic compound, but it's the same process. Assume you have a 100-gram sample, divide by atomic mass to get moles, do a ratio of moles, and that ratio, that final ratio of moles, tells you what your subscripts are. And then the last one, number 40, will give you an empirical formula and the true molecular mass of a compound and ask you to identify what the molecular formula is. And that is simply where you do that one last ratio step, go back and look at the pencast. There are quite a few problems related to math, or that you'll be using your math skills on this part of the test, but you're going to see more of that on your honors page, and I know you guys always want to know about the honors page. So you're going to find that the questions that you're doing on the regular test are really pretty straightforward, just the basics. On the honors page, we're going to put those into context. And I'm going to give you lab situations. It will be like your hydrate lab. It will be like the tin oxide empirical formula lab, where you'll have to go through those kinds of calculations Instead of giving you just the mass of the elements involved, I will be saying, well, Susie and Bobby went to lab and they measured the mass of a crucible, and they added 5 grams of magnesium sulfate to it. They heated it and drove off the water. The product that was left had a mass of this. Calculate the empirical formula for that hydrate. So in that situation, you need to remember to subtract away the mass of the container, look at the masses of just the chemicals, the ionic compound, and the waters of hydration that are attached, and apply it there. Don't be surprised if I ask you to calculate the empirical formula for some really weird compound, a really weird organic compound that you've maybe never heard of or is kind of gross or something. It's all the same process. If you're given the percents, assuming you have a 100-gram sample, convert to moles, do a mole ratio. When in doubt, convert to moles. That's what stoichiometry is all about. And there's, I think, 5 or 6 problems on the first part of your honors page. The second part of your honors page, I'm actually going to divide this into 2 days just so you have enough time to work through the math. Some of you are going to buzz through that pretty quickly. Some others of you like to take your time. So we're going to split it into 2 days just so you're not overwhelmed. The second part is going to be about naming and formula writing, where you'll have to use both systems, the stock system and the classical system, the us and ic endings, to show oxidation states, say, of transition metals and heavy metals that can have more than one oxidation state, maybe a little bit of acids in there, and part of that is going to be redox. And you might be saying, oh my gosh, we did that whole redox chapter, we had Leo and Gur before, why do we have to keep doing that? Well, we're going to be balancing equations soon, and there is a way to balance equations by redox. A lot of our reactions take place because of oxidation and reduction, or that oxidation and reduction are involved. You still need to know that. Knowing redox and how to write half reactions is constantly reinforcing what the oxidation numbers are of compounds, and that's what's helping you write formulas in this chapter, and it's going to help you write formulas correctly in the next chapter when we start stringing all these things together and writing balanced equations. So go back to chapter 19, look at how to write half reactions, do some practice on those. We have a couple worksheets there that we just did some of the problems. You have more to try for practice. That part of the honors page will look very familiar. So make sure you go back and do those. Happy studying. Thanks for watching. Learn your polyatomic ions and be awesome.